work now?
Okay, yes, I'm recording. Then, yeah. Okay, welcome everybody to our Prague Mathematical Physics Seminar. The speaker for today is Lukas Müller, who's a postdoc in Bonn and who's gonna tell us about the symmetry defects in two-dimensional Yang-Mills theory, twisted bundles, and quantization. Please, Lukas.
Yeah. Okay, let me first of all start by thanking the organizers for the opportunity to present my work and everyone else for listening and showing up. And also by saying that if you have any questions, feel free to interrupt me at any time. So I'm going to talk about joint work with Richard Szabo and Laurent Segedi, which is related to certain defects in two-dimensional Yang-Mills theory and their connection to twisted bundles. And then in the last part, I will talk about joint work in progress with Corinna Keller, where we work on constructing quantizations of these moduli spaces of flat bundles. So the brief outline for my talk is that I will start with discussing what symmetry defects are and a simple class of examples in Yang-Mills theory. Then in the second section, I will explain their connection to geometry in terms of twisted bundles. Then there's a largely independent section, which just explains how to reformulate some of the results within an axiomatic approach to quantum field theory known as functorial field theories. And finally, I will come to the quantization of these moduli spaces. Okay. So let me start with a really brief introduction to how I think about defects in a quantum field theory. So naively, a quantum field theory, you can mathematically think of a tool which you put in a space-time manifold M, and it gives you back a complex number, which is the partition function, which is somehow should be computed as a path integral over some space of dynamical fields. And a defect in the quantum field theory can be thought as some kind of extended observable. So now you do not only put in a manifold, but you put in a stratified manifold. So it's something where you have embedded submanifolds and something weird can happen on them. So for example, you can have fields which jump on the submanifold, or you can just have something like a Wilson line where you just change the partition function by adding the holonomy along the loop into the path integral. And this is somehow the general picture to have in mind. And we even allow to have, if we have a defect of codimension 1, we even allow to have like different quantum field theories on different regions. And another important example are boundary conditions, which you can think of as a defect between a trivial theory and the theory you consider. But you should just think of this as something you can insert into your field theory, which somehow changes the output. And I will discuss a really precise example of that in my talk. Okay. But before that, I want to connect defects to symmetries. And for this, I'm not considering general defects, but some of a specific type. So the first condition we impose is that they are topological, which just means that the insertion only depends on the submanifold up to continuous deformations. So the value of the partition function agrees if I continuously deform, let's say, a wiggly line into a straight line. And the second type of defects are invertible defects. So if you have two defects, you can try to construct a new defect by doing the following operation. You take the two defects, you put them really close together, and you take the limit where the distance goes to 0. And if you are lucky, this defines a new defect. In particular, this limit always exists if it's topological. And then a defect is invertible. So a defect D is invertible if there exists another defect, D to the -1, such that this fusion operation gives the trivial defect. And this is a defect which, when you insert in the theory, just does nothing. So it's the same as not inserting any defects at all. And this is a defect you always have in any quantum field theory. Okay. So how are these things related to symmetries? If I have a symmetry in my field theory, what I can do is I can construct an invertible defect which acts on a field insertion which passes through it by applying the symmetry. So somehow the left and the right of the defect differ by the symmetry. And you might think that this is something which doesn't do anything, but actually since these defects somehow are local in space, this is similar to gauging the symmetry, as we will see in a bit. So I can go from a symmetry to a defect, but I can also go the other way. If I have a codimension 1 defect and I have a field insertion, I can try to act with the defect on the field insertion by just wrapping the defect around the field and then making this sphere around about this point insertion really small and define a symmetry action in this way. And not always, but if you have some nice conditions, this will give you an equivalence between defects and symmetries. Okay, so that's the general picture I have in mind, and now I want to make this precise in the case of really simple symmetries in two-dimensional Young-Mills theory. So let me set the stage by fixing some notation. So we fix a semi-simple compact Lie group, which has a Lie algebra G, and we fix the Riemannian surface. And then the fields of Young-Mills theory are principal bundles over the surface with connection. And the action functional is just given by taking the trace of the curvature ratchet with the Hodge star, and then integrating over the surface. The trace here is a suitable normalization of the killing form on the Lie algebra, and then there's a coupling constant in front. And what one wants to compute in the quantum field theory is now the path integral over all bundles with connection up to gauge transformation of this exponentiated action. And in 2 dimensions, this is actually exactly computable, as we will see in a few slides. And it turns out that this only depends on the area of the surface. So in general, this would depend on the whole Riemannian metric you fix on sigma, but in this case, it only depends on the area, which means it's nearly topological in the sense that it only depends on one parameter you can form out of the metric. And this allows you to axiomatically treat it similar to a quantum field theory, which I will talk to a topological field theory. And I will talk a bit about that in section 3 of my talk. Okay, so now we want to build a symmetry, but somehow we want to build a symmetry which is not specific to any space-time, but something which you can do on always. And so in a more formal sense, we look at symmetries coming from automorphisms of the stack of G bundles. But what we are going to do is quite concrete. So what we use as an input to construct a symmetry are just outer automorphisms of the group. So these are automorphisms which are not given by conjugation. And an example of such an automorphism is complex conjugation from SUN to SUN as soon as n is larger than 2. And now having such an automorphism, we can take its derivative at the unit, which induces a Lie algebra homomorphism from G to G. And then we can, so the action on the field configuration is just by forming the associated bundle along this group homomorphism, but we can also be more precise what this means. So we act on a field configuration, which is a principal bundle with a connection, which we can describe as a one form on the total space. And we act on this bundle by selling it to a new bundle, where now the action is not the right action of the bundle is not the one we had before, but it's twisted by first applying phi to the -1, so the inverse on the G part, and then the old action. And for the connection, we just use this induced morphism on the Lie algebra part of the connection. So we get a new one form with values in the Lie algebra on the total space. And one can show that, or then it directly follows that the action transforms as follows. So you take the action, and the only thing which happens is that you apply the morphism on the Lie algebras to the curvature. And then you take the trace, but the trace is a multiple of the killing form, which is always invariant under outer automorphisms. Okay. So I told you that there are symmetries corresponding to these outer automorphisms, but so now we want to maybe ask, do they exist? How many are they? Are they interesting? And they actually have a really nice and useful classification. So by differentiation, we can get outer automorphisms of the Lie algebra. And these are actually classified by symmetries of the underlying Dinkin diagram. So for example, here there's the Dinkin diagram D4. And then symmetries are just maps which map nodes, exchange some nodes. So here we have an S3 symmetry, which just exchanges the outer nodes. And you can never exchange the inner node with any outer node because it would not preserve the structure of the diagram. And then this acts on the Lie algebra by just exchanging the different copies of SU2 you get for every node. So for every node in the Lincoln diagram, you have like an SU2 copy in your Lie algebra, and you just exchange them. And then here in the table, there are just some examples of these groups. So they are usually quite small, and the most interesting one is D4, where it's non-abelian and you get the symmetric group on 3 elements. And this realization actually has a useful consequence, namely that we can form the semi-direct product. Because in general, the group of outer automorphisms is not a subgroup of all automorphisms, but just a quotient. And this construction gives us a section, so we can actually coherently realize them as outer automorphisms. And then we can form the semi-direct product group, which has as elements just the usual product, but the multiplication is twisted in the following sense. So the multiplication of 2 elements like this is on the outer automorphism is just composition, but then we move this G prime past the phi, so we act with it on the G prime. And this group will be important later on when I come to twisted bundles. Okay, so far I just talked about the classical theory and the classical symmetry, but sometimes if you have the classical symmetry, this does not extend to the quantum theory. But here we can actually show that it does using the lattice regularization of 2-dimensional Young-Mills theory, which has the nice property that it's actually invariant under refinement of the lattice, so it directly computes the continuum limit. So you just pick a lattice and you get an exact result for the position function. Yeah, and most of what I'm now going to tell, I learned from a paper by Witten. And a lot of things I'm going to talk about are just slight generalizations of what he did, at least here. Okay, so let me briefly explain what lattice regularization is. So we have our surface sigma here, which in this case is a torus, and we pick a triangulation or more or less a decomposition of it, where we also allow polygons which have more than 3 edges, like a square here. And then the Riemannian metric, now the only thing which is left over from it is an area for every triangle. And principal bundles on this discretized space, we can now, with connection, can now be described by assigning a parallel transport to every edge. So here are 3 edges, and we assign a group element to every edge. And then the path integral just reduces to an integral over as many edges we have copies of G. And the integration measure, we just choose to be the H integral, or the measure induced from the H integral on the group. And then the only thing which is still open is to what we want to integrate. And formally, we can already see that this should decompose into the different triangles we have. So there should be like a contribution for every phase we have. And then what this should be is the partition function of Young-Mills theory on a disk, which actually has been computed before. So in general, this should be a function which is gauge invariant. So the only gauge invariant quantity we can form is the holonomy around this triangle. And then so it should only depend on the holonomy UI, which is the product. And it turns out that what one should choose is the following sum over simple representations of the group. We take the dimension of the representation, we take the value of the character on the holonomy, and then we weight this with an exponential factor depending on the area times the quadratic Casimir operator in the representation, which for SU2 would just be the total angular momentum. Okay, and now how does the symmetry act here? It just acts by applying the automorphism to all group elements. So so this is how we act with the symmetry. And now we can ask if this is invariant. And first note that the H measure is invariant just because if you act with phi on it, you get a new measure, which is also G invariant and normalized. And since there's only a unique measure on the group, this will be invariant. And then we can ask if this expression is invariant. But here we just act with phi on the UI. This is the same as evaluating the character of the pullback representation. So this is this is not equal, this goes to. And then the invariance just follows because the dimension and the Casimir operator and the pullback representation agree with the original one. So we have seen that the symmetry actually extends to the quantum world. And now let me also mention how to implement the defects. So now we are in the following situation. We have a torus again, and I picked a simple decomposition of it. So what we should do in the path integral is we should integrate over two group elements, G1 and G2. But now, in addition, I want to put a symmetry defect here. And what I need to do now is when I'm on the left of the defect, I just want to use the group element. But when I'm on the right, so when I'm over here, I want to act with the symmetry. So I take the same expression as before, but when I compute the holonomy, I just, this is now G1 times G2, G1 inverse. And now here, I don't use G2, but I first apply the symmetry. So I use phi of G2 and then the inverse. And I go down here. And then one can compute this expression just using the usual orthogonality relations for characters. And one finds that this actually gives a sum, but not over all representations, but just those which are invariant under the outer automorphism. So for example, for SUN, this would be a sum over real representations.
Sorry, can I ask a question? So this is probably obvious or something, but why is that defect just applied on one of those lines if they are identified? Like, why am I not applying the phi on both of G2s when I'm going around the holonomy?
So the thing is, I mean, there's just one defect which I just put on the side which I just put on the edge I have here. But then, so you should actually think of this as like this G, there are somehow two G2s. There's like one which sits here and one which sits here. And usually because they are really close together, nothing happens. But now I'm here, I'm on the left of the symmetry. So what I want to say is the connection somehow jumps when I cross this line. So there's a jump given by applying phi.
Okay.
So so the thing is that we somehow put the defect on the edge, but what I probably should have done is like put two edges like this and then glue along something in the middle, but you would get the same in the end. So it's really just, I mean, the idea is just if you're on the left, you just have like the thing you have on the left and the thing you have on the right differ by a jump, which is given by the outer automorphism.
Mm. Okay. Thanks.
I hope that helps a bit. Okay. Are there any other questions for the first section? The next section is just to describe some kind of geometric object such that you can realize this partition function as a path integral over these geometric objects. So they are, that's what I'm going to talk about. They are called twisted bundles. But so first, to come to their definition, I need to briefly motivate how you can use a symmetry network to build a principal out G bundle. So, and for this, one motivation to do this is gauging. So if you want to have a symmetry and you want to gauge it, you want to couple your field theory to non-trivial background fields. And if your symmetry is a Lie group or so, you can use minimal coupling type things. But if it's just a discrete group, there's no connection. So the coupling is somehow, this will just give you 0. But what you can do is you can somehow use the symmetry defects to construct the partition function coupled to a non-trivial background gauge field. And the way you do that is you just realize that if you have a defect network described by symmetry defects, which I now also allowed to meet at some point, where I want to impose some compatibility conditions, then I can build a principal out G bundle from that by just putting a small open neighborhood around every phase of the decomposition induced by the defect network, and then use the the labels on the edges as transition functions to define the bundle. So we define a bundle using this defect network. And then for this to actually give you a gauging, you need to make sure that somehow there are a lot of defect networks which gives the same bundle, but you need to make sure that this is independent of the choice. But you can do that. And so this is sometimes known as the defect approach to orbifolds. So defect orbifolds. And we write a lot about that in our paper. So the paper with Richard and Laurent, but I'm not going to talk that much about it here. Okay. So all I want you to keep in mind is that from a defect network, I can construct a principal out G bundle. And now I also want to recall the exact sequence for the semi-direct product here. And I can use this map, the projection map down here, to induce a map between the spaces of principal bundles. And then we can give a definition of a D-twisted G bundle. So D is the bundle built out of this, the out G bundle built out from the defects. And we say this is just a lift of this D bundle to a G semi-direct product out G bundle. And since we work with bundles, you should never say it's a strict lift, but you should say it's a lift up to a gauge transformation. So it's a principal bundle P for this large group, together with an identification of applying this map here to P with D. So there's some gauge transformation. And then we introduce a notation for the space of all such bundles with connection. And sometimes I want to consider the space up to gauge transformations. And sometimes I just want to consider it as a space with G action. And then formally, one can note that if I now have such a twisted bundle, the space of connections is an affine space over the sections of the adjoint bundle, now adjoint to P, but the Lie algebra is still the same because this thing, the identity component of the larger group looks the same as the one of the smaller one. And then the second thing to note is that at least formally this space has a symplectic form, which is just given by taking two tangent vectors, wedging them together and evaluating the trace. And I mean, since it's an affine space, this is just the tangent space. Okay. So I introduced these geometric objects. Now I want to justify that they actually encode the symmetry. So for that, what we do is we take such a twisted bundle and we describe it with respect to the same open cover as we have chosen here to build the bundle D. And then since it's a G semi-direct product out G bundle, like the transition functions are of the form Gij and then some outer automorphism. But these things are completely fixed to be the fixed by D. They just need to be with the transition functions of D, or at least up to a gauge transformation. You can assume that. So I mean, there was this freedom, but you can always choose them to be there. And then now, if you write down the two co-cycle condition in the larger group, this is not just going to give you the usual co-cycle condition, but one where you need to act with the symmetry on the Gji. And you can think of that as applying the symmetry on the transition function when it goes through the defect. And then the second thing, you can look at what happens with connections. So locally, you can describe them by one forms in the Lie algebra. And then if I now assume that I'm in the situation where these things are trivial, just to make the formula a bit easier, then we see that AI is related to AJ by using the adjoint action of 1, phi ij. But then if I conjugate something in the identity component of the semi-direct product with an outer automorphism, I just act with the outer automorphism on it. So this means what I do is I just apply the derivative of this outer automorphism to the AJ. And this is exactly the transformation behavior for connections we have seen before. So these bundles somehow implement the symmetries geometrically. So somehow you can think of these as G bundles, but then if there's a defect, it jumps by the symmetry. So it's somehow discontinuous, but the jumps are controlled. And so we propose to realize the partition function in the presence of a defect network as the path integral also over the space of all twisted bundles. And you can just use the same Young-Mills action function, but now for the larger bundle. And so this proposal actually leads to a non-trivial conjecture, because now I have given you like a concrete way to compute it in lattice regularization, and I also have given you a geometric interpretation. And following the work of Witten, a good idea in this situation is to look at the recoupling limit. So remember, we had like something like 1 over 4e squared. So if I look at the limit where e goes to 0, which turns out to be the same as the 0 area limit, then we see that this prefactor diverges. So as soon as I have a field configuration where the action is non-zero, this will be just weighted with with 0 in the path integral. So the path integral now localizes to the space of fields with 0 Young-Mills action, but these are just the flat bundles. So in this limit, one gets the localization to the space of flat twisted bundles, and so and what one integrates is 1. And now this, so we integrate 1 over a space, so this should give us a volume, and this should be the symplectic volume of this moduli space, which is actually a mathematically well-defined object one can study and try to compute. And then you can compare to the computation using lattice regularization. And we managed to actually evaluate this for SU3. And then if we are on a surface sigma, which at least has one non-trivial defect, the partition function turns out to be some zeta function, G is the genus. And then there's this one constant, which is somehow a choice of renormalization scheme. And this shows up in the similar computations of Witten for the symplectic volume of ordinary moduli spaces. But this is something so this is just one constant, but there are infinitely many spaces. So this is a conjecture one can actually try to prove. Okay, and since I already started talking about flat bundles, I will now give you a more hands-on description. I mean, you probably all know that flat G bundles on the surface can be described by representations of the fundamental group up to conjugation. And the same is true for twisted bundles, but with a twist in the representation. So first, the out G bundle we use to twist is just described by a group homomorphism from pi1 to out G. So this is just, so here's a picture of a surface, and then pi1 is just generated by all these loops you can see here. So this just assigns an outer automorphism to every loop. And these are somehow dual to the description we had before. So before we had had some defects where I had some pi ij, and now I have a loop, and this is the loop which also gets labeled with phi ij. So it's like the holonomy from one center to the other one is given by the transition function. So we have this twisting thing down here, and then twisted bundles can just be described by lists. And one can just write out what these lists mean if you want to describe them only in terms of G. So they are maps of sets from pi1 to G, which satisfy this twisted compatibility with composition. And the action of through gauge transformations of G on this is now not given by conjugation, but you need to twist the conjugation on the right. And this is, for example, also the description of flat twisted bundles, which appears in the work of Meinrenken.
Sorry, can I ask a question here?
Yeah, sure.
So this row, that's the thing that was the capital D before, right? It's
yeah, the row is the map describing D. Yeah, exactly.
Thank you very much.
Yeah. I think I later on will change the name for it again. I'm sorry about that, but I will comment about it as well. Okay, and then, so the last bit of this section is just to mention a slight generalization, which is in the context of what is known as a fractionalized symmetry in condensed matter systems. So what can happen if you have a symmetry group D? Now D is not a bundle but a finite group. Then what can happen is that the action of the group does not close on your field configurations, but it only closes up to gauge transformations. In this case, you get some interesting interaction between the action of D and the gauge group G, which can be encoded in an exact sequence like this. So then the symmetry will be described by giving an extension G hat of D by G. And these extensions can be described by what's known as a non-abelian Tuco cycle. So this is a map of sets from D to the automorphisms of G. How do I get such a map from an extension? I just pick a section here, but just a section of sets. And then I can act on an element in G by conjugating with the lift. And then there's also a different part of the Tuco cycle, which is a sigma, which just tells you how this lift fails to be a group homomorphism. Because if I now lift the product of two elements, it might not be the product of the lifts, but the difference will live in G. And this is this function here. And these two data completely describe the extensions. And they also, at least in the discrete case, describe all symmetries of the stack of G bundles. And then we can define twisted bundles as before, as being lifts. Now I have a D bundle on my surface, and I can ask it to lift it to a G hat bundle. And we can write down what it looks locally. And there we get, again, a twisted version of the transition functions. But now, I mean, this term we had before, but there's this additional term which comes from the fact that the sequence is non-split. And then for the connections, it has the same. And if you look at this formula a bit, you see that this is nothing else but sections of a non-abelian job with structures two groups, the two automorphism group of G. Okay. Are there questions until now? If not, I will now start talking a bit more about the formal, I mean something more formal, or an axiomatic approach to quantum field theory, and how to realize some of the things I talked about until now in this framework. So this section will be slightly independent of the previous one. So if you are lost, now is a good time to start listening again, if you want to. Let me start with a really brief motivation of this approach, which goes under the name of functorial field theory, which goes back to the work of Atiyah and Siegel. And the idea was to, even though you cannot define the path integral in all generality, you try to somehow axiomatize the properties you get out of the path integral. And for this, I should set up a bit more structure. So if I have an n-dimensional field theory, this is something I want to be able to evaluate on all n-dimensional manifolds, but those might need to be equipped with some background structure. So for example, to evaluate Yang-Mills theory, I need a metric. And if I have spinors, I probably need to pick a spin structure. And sometimes there are some principal bundles you need to write down your action. Or if you integrate something, you probably want to have an orientation, because otherwise you would need to work with densities. So there's a collection of background fields I call F. And then there's a space of dynamical fields. These are the fields I want to perform the path integral. And then the field theory should not just assign numbers to manifolds, but also Hilbert spaces to time slices, which I just think of as n-1 dimensional manifolds, which also come with background fields. So what I want to, the Hilbert space I want to assign to these is the space of square integrable functions on the set of dynamical fields. I mean, this is highly not well defined, but just let's go with it and see where we get. That's somehow the idea. And now the thing one wants to compute is this partition function. For that, it's an integral over the dynamical field of some action functional, which depends on the background field. Yeah. And we can now try to study what happens if I start decomposing my manifold into simpler pieces. So, for example, so this somehow should be related to locality. So if I start cutting along these red circles here, I get the following situation, and then I have now I have some n-1 dimensional manifolds here. So to those I want to assign a Hilbert space. These Hilbert spaces, and then I can use the path integral to. So now if I look at the path integral on these pieces, they will not just be numbers, but they will actually be linear maps between the Hilbert spaces I assign. So for example, to this piece, I want to assign a map from C to the Hilbert space assigned to sigma 1. And what this should be, it should so it should just be an element in there. So it should be a function on the fields of boundaries, on the space of boundaries. Right? So if I have a boundary field phi, I can just send it to the number, which is now a path integral over the space of fields on M1. And then, but I impose the boundary condition that it restricts to phi. And then I integrate the action. And this will be a function. And similarly, one can define linear maps between these Hilbert spaces, at least formally. And that's the whole idea, that maybe we cannot define the path integral, but maybe we can just say it consists of all these maps for all these manifolds. And then one has some kind of structure one can study, and in simple cases even classify, as we will see now. So, no, there's one more thing I wanted to say, and then I have all these linear maps, but at least formally it turns out that if I compose all these linear maps, I get a map from C to C, which I can identify with a complex number, and this number computes the original path integral. So these maps are somehow compatible with Gluon. Okay. And now one can make this into a definition. Quite generally, there are a lot of technical problems I don't want to talk about, but this is one approach, and I will just now give the simple definition needed for two-dimensional Young-Mills theory. And as we have seen, this only depends on the area. So our background structures are just an area and an orientation. Okay, and for this, we define a symmetric monoidal category of cobordisms with area. The objects are just circles or disjoint unions of circles, and the morphisms are bordisms. So these are two-dimensional manifolds with boundary, and they are a morphism from one boundary to the other one, similar to the picture we have seen before. And composition will just be by gluing along boundaries. And the only additional data is that every connected component of a bordism comes with a positive real number, which is the area. And then this becomes symmetric monoidal by taking disjoint unions of manifolds. So then we want to describe a field area-dependent field theory as a functor from this category to the category of Hilbert spaces, which is just saying we want the structure I talked about before. And then there's one additional thing one should require, which is that it's continuous in the area. So we want this map to be continuous in the area, which means that so if I vary the area a bit, the value the bounded operator I assign to it also gets varied a bit. And the topology one needs to use is the strong operator topology. And then, as I said before, the advantage of having a definition is that one can try to classify these things. And there's a theorem which classifies these in terms of regularized commutative Frobenius algebra. So if we have seen the classification of 2D topological field theories, this is a slight generalization to functional analysis of that. And I will define them in a few moments. Okay, but first, let me also mention how to include defects in the picture. So as I said before, or in my motivation, for me, they are just some insertions you can put. So I can just define a category, an extension, which now contains defects as well. So the objects are, again, circles, but now they come with marked points. And these marked points might carry some labels, D1 and D2. And the morphisms are, again, morphisms, but now they come with a stratification. So there are some embedded submanifolds which might meet at some point, and everything carries labels. And then composition is again by gluing, and disjoint union is again by disjoint union. And the defect area dependent field theory is just a functor out of this. Okay, before I can tell you what the regularized Frobenius algebra is, I need to recall the graphical calculus. I mean, just to simplify some formulas, I use the graphical calculus for Hilbert spaces. So for a bounded operator, I just draw a line, and then I put a box and write f. So f is the bounded operator, and this is goes from A to B. For the tensor product, I just write them next to each other, and I use this crossing to denote the usual crossing in Hilbert spaces. And now a regularized Frobenius algebra, not necessarily commutative, is you just take the definition of a Frobenius algebra and you make everything depend on a non-negative area parameter. So you get a bounded linear operator from A tensor A to A for every small area parameter small a. You get unit maps, you get co-unit maps, you get co-multiplications and co-unit maps, and all of them depend continuously on the parameter. And then you impose the usual relations. So for example, associativity, that's what you can see here. And you impose this relation as soon as A and B, the sum of A and B is equal to the sum of A prime and B prime. And you should think of this multiplication as just being the value of the field theory on the pair of pens with area A. So this corresponds to this multiplication. Okay. And then there are relations for the co-multiplication and so on. I'm going to skip that and just present the one example one actually cares about, or the one example relevant for two-dimensional Young-Mills theory, which are the square integrable functions on the group. The unit is the partition function on the disk we have seen before, because I mean, this also makes a lot of sense because that's what you assign to a disk in your field theory. And then we can define a non-area dependent product just by the convolution product for functions. And we get the area in by using a convolution with the area dependent unit. We define the co-product and the co-unit just to be the adjoint. And then the commutative Frobenius algebra describing Young-Mills theory is just the center. So these are the class functions on G. And that's what you would expect, because the space of field configurations on a circle are the principal bundles, but they are completely described by the holonomy up to conjugation. So this is exactly class functions on G. Okay, and I will probably skip these things. All I might want to say that one can define bimodules in the setting, which then will correspond to defects, and one can define two bimodules. One can define two types of bimodules, one corresponding to Wilson lines, and the other one to these twisted defects I have introduced at the beginning. And if you want to see more about them, I recommend looking at either my paper or the paper by Ingo and Laurent. Okay, so let's come back to the geometry of twisted bundles, and in this case of flat twisted bundles. I mean, so far I did mostly talk about the non-flat version, but which is important in Young-Mills theory, but if one wants to look at things like Chern-Simons theory, other things one also wants to understand the flat case, and especially quantizations of its moduli space. Okay, so first, I want to give you a more hands-on description for the Poisson structure on those. And this can be easily deduced from work of Fogg and Rossley, at least when the surface has at least one when the surface has a boundary. So if I have a surface which at least has one boundary, then I can do the following. I can combinatorically just describe it by a graph. You can see here, which comes with a ordering of its half edges. So there's like some ordering of these edges. I go on here, and then from this graph, I can reconstruct the surface by just thickening up the edges and then gluing them to the point, which I also have thickened up to a ball, using the ordering, and then this will turn out to be diffeomorphic to the surface. And now, as I said, now I'm changing conventions again a bit, sadly. So the out G bundle can be described by just assigning an outer automorphism to every edge. I mean, the fundamental group of this graph here is the same as the fundamental group of the surface over here, and it's free on two generators. So I just need to assign two elements to it, and then the moduli space of twisted bundles can be described by also just assigning two elements to every edge. So I have something like G and G prime. And then the action by conjugation just gets twisted. So the gauge transformations act by sending this to H, G, kappa, H minus 1. And this is the quotient one wants to take. And one way to get a Poisson structure on this space is just to realize that these twisted bundles, they sit inside the space of all G semi-direct product out G bundles. And then E is just the number of edges. And depending on a classical R matrix for G, Fogg and Rossley construct a Poisson structure on the space. And we can just pull it back using this embedding here, which sends a pair of group elements to these elements in the semi-direct product, which is a local diffeomorphism just because this group is discrete. So we get an induced Poisson structure. And now I want to talk in the last few minutes about how to quantize them, or one approach to constructing a quantization for these spaces, which follows the work of Bentry, Boucher, and Jordan. So the idea here is not to pick a specific space and construct a quantization. I mean, this is quite probably also possible because these things are not too hard, but we somehow want to quantize all at once. And furthermore, we want to somehow only quantize them locally and then use this to glue things back together to get a quantization of larger things. Somehow we want to have a quantization which is coherent and compatible with decompositions. So one might want to try to consider somehow not an object of one object, but quantization of this functor here, which sends, so this is a category of two-dimensional manifolds equipped with principal out G bundles. So this is a manifold, objects are a manifold, and then a principal bundle phi. And this gets mapped to some type of spaces, which I'm not going to be precise about, and just sends it to this moduli space of twisted bundles on sigma. And then I can map it to the functions on this space, which is Poisson algebra. So I could try to deform this whole functor at once. The problem is that if I want to do this to be compatible with, or to be constructible from local data, I more or less can give up, because locally, the space of bundles is just a point. So if I look at the space of twisted G bundles on a point, or on a disk, then this is just a point, because all bundles over a disk are trivial. And then the functions on this are C, and I'm not going to get many interesting things to study. And the problem here is that somehow we have forgotten, we have like this, if we consider this object as a space, we have taken a quotient by the gauge transformations. But quite often, if you want to make things gluing constructions work, you should not do that, but rather remember these gauge transformations and treat the object as a Lie group fault, which then means that this thing is something stacky. So one should treat this as a stack. But then if we are in the world of stacks, we should, like if we then take functions on them, depending on what you mean by it, you just end up with this again. So you should probably also try to deform something else. And what one takes is quasi-coherent sheaves, which one can think of as vector bundles over the space. So what we try to quantize is a functor which goes from this category of manifolds without G bundles to a certain category of linear categories, and it sends a manifold to the category of quasi-coherent sheaves in the space. And also let me give you a different way to think about quasi-coherent sheaves, which is actually the one relevant for us. So if you have an affine space, which is described by an algebra A, and you have a G action on it, then the quasi-coherent sheaves on this corresponding quotient stack are just representations of A, but inside the representation of G. So these are just representations which come with compatible representations of G. And now, so coming back to the locality business, now one could hope that this is something like a co-sheaf and then just deform it locally and one is done. The problem is that this is not a co-sheaf, at least not as written here, but it satisfies a different type of locality property, which is described by something called factorization homology. So we have like this large category on which we have our quasi-coherent sheaves. And we want to be able to somehow reconstruct it from something locally. And the local thing is a category of disks. These are two-dimensional manifolds which are disjoint unions of disks and all equipped without G bundles. And then the morphisms are just embeddings, which might be combined with G, with gauge transformations of the bundles. And the statement is that for the quasi-coherent sheaves, if I just look at this restriction to out G, I can reconstruct the value on the whole manifold by computing what's known as factorization homology, or as a left Kahn extension here. So there's like a universal way to extend such a functor to a functor here along this embedding, which one can write as a co-limit about all ways of embedding disk into a larger one. But this is not going to be super important for us. This is just like a formal thing you can do and something you can actually compute. But now what's more interesting are what are these functors here? And they actually have been studied for a long time. They are known as, in this case, out-G disk algebras, and they have been classified a while ago in a slightly different language by Salvatore and Val. And they said a functor like this just corresponds to what's called a balanced braided category, which comes with a compatible out-G action. So you don't even need to know what a balanced braided category is. I'm just going to show you two embeddings which will give some structure. And this is all one needs to know, because I'm more or less done anyways. So I can consider an embedding of two disks into a larger one. And then if I evaluate this A on this embedding, I get a tensor product functor from two copies of what I assign to a disk to one disk. And it's important to require this thing to be symmetric monoidal. So this will give me a tensor product. And then I also have a homotopy of this embedding, which just moves this disk here and this disk there. And I can evaluate my functor on this, which will give me a natural transformation, which is the braiding. And the action of an automorphism is just given by considering the identity embedding, but using a gauge transformation corresponding to an outer automorphism. And this will give us an action on this category C. Okay. And now our strategy for quantization is just to quantize this local structure and then compute factorization homology. And so that's what we do. Like, as I said before, locally, this space is just a point on which G acts. So the category of quasi-coherent Gs is the category of representations of G. And then the out G action is just by pulling back the representation along the outer automorphism. And this is symmetric monoidal, which is sometimes called an E-infinity category, so E-infinity algebra, which means it's as commutative as it could be. And then a well-known quantization of the category of representations of G are just modules over the quantum group. And since we can realize this out G action by Dinkin diagram automorphism, can actually act on the quantum group, and then via pullback we get an induced action on this category of modules over the quantum group. And this is less commutative. This is only an E2 algebra, so it's braided, and there's actually, we lost a lot of commutativity. So this is what quantization should do. Should replace a commutative object with something less commutative. Okay, and now there are two more slides. So the strategy for quantization is now to start with this category of modules over the quantum group and compute factorization homology on surfaces and hope that this actually gives the quantization. That's what we do, and so that's the joint work with Corinna, where we even show something more general. So you can start with a quasi-triangular Hopf algebra H, which comes with an action of a group D. Now D is again a group. And then for a fixed element in D, one can define a new algebra, which is as a vector space, it's the restricted dual of H. So it's a category of matrix coefficients on H. And then it gets a multiplication, which is more or less the multiplication on Majib's twisted double. But there's an additional twist, which comes by acting with D on this R matrix element. I mean, I just wanted to show you that there's a concrete formula. I don't want you to understand that right now at all. And then the theorem says that you can describe factorization homology on a surface like this, which comes with a D bundle described by these two elements, doing something similar to the similar. And yeah, doing the following, you just assign to every arc, you assign the algebra FD. So here we assign FD, here we assign FD prime, and then we take the tensor product over all these algebras, and we define a multiplication on it using the gluing pattern. And then modules over this algebra within the category of H modules will compute the factorization homology. And the last statement is now that if you look at this for the quantum group and you consider everything formally, so you work with formal power series in H bar, then we can compute this algebra, and this actually quantizes the Poisson structure on G to the E, which corresponds to these twisted bundles. And furthermore, since everything is equivariant with respect to the action, I can look at the algebra of invariant, and this gives the quantization for the Poisson structure on the moduli space. Okay, that's all I wanted to say. So thank you for your attention.
Thank you, Lucas. I think we can unmute ourselves and give you a round of applause. Are there further questions?
I have maybe one super stupid question. So when you're constructing that surface from the ribbon graph, like from that graph where you are like choosing the order of the half edges or edges adjacent to it, you always will have at least one boundary. So what if you want to assume something without a boundary? Can you like somehow glue these surfaces or?
Yeah, exactly. I mean, so like the Fogg-Rossley thing doesn't work. What happens is, I mean, what makes this situation extremely nice is that the fundamental group of this graph is always free. So there are no relations if you look at its representation. And this also allows this theorem, which says that we can describe them as modules. over a simple algebra, what you can do is, I mean, if you have a surface which looks like this, and then you have a different, and then you can just glue in a disk like this. Okay, my drawing is extremely bad, but so what you can do is you can glue in a disk like this. And so in factorization homology, these gluing things just tell you that you need to compute a relative tensor product. So you have like, you get a category here, you get a category here, and then you have like for the disk, you get an algebra A, and what you want to compute, I mean, you get an algebra within linear categories, and you want to compute this relative tensor product. And actually, you can realize this as certain modules over a different algebra. So you can compute this. The problem is, I mean, this is not just the problem in our case. It's somehow to relate this to known quantizations of modular spaces of bundles on closed surfaces. So I think that's also not done in the work by Adrian, David, and David. So we can compute the factorization homology. We just don't know if it quantizes anything known explicitly.
Isn't the closing of the caps in their second paper?
Yeah, they computed.
Okay,
they computed in the second paper. I think what's not so clear is what it actually quantizes.
Okay.
Because
whether it corresponds to the moment maps, right?
Yeah. I mean, these things here, I mean, instead of gluing this thing in, you can also, in the classical case, you do like a Hamiltonian reduction. And then this thing is a deformation of that. So it's quantum Hamiltonian reduction, but yeah. But yeah, you can do this gluing, you can compute what you get. I just cannot write down a precise Poisson algebra which gets quantized by that. But maybe it's somewhere in their papers.
Thank you.
Yes, please, Jan.
Sorry, wait. Okay, good. You talked about the surface of this, about the area of the surface, yeah. But now it doesn't appear here in this.
That's because it's a flat case. So this is like the area goes to zero limit.
Okay.
Because now, so I should have made that clear. Starting here, so before these were all bundles, not flat, and then you need to do the area. Mm-hmm. But from here on, I just look at flat bundles. So I more look at something like the value of Chern-Simons theory on 2D surfaces.
Yeah, okay, that was exactly my question. So, like, in some sense, this is the common point with Chern-Simons, where
Chern-Simons, okay. And then also Kapustin-Witten in some sense, at least. That's what is claimed in the BZ.
Mm-hmm. Okay.
But yeah, no, I should have been clear about that. Like these moduli spaces, somehow they're only nice geometric objects if it's flat.
Mm-hmm. Okay. Yeah, thank you very much for a nice talk.
So I don't see further questions. Therefore, I think we can thank warmly Lukas again for the very exciting talk.
Yeah, thanks for listening. Thanks for the invitation.
Yeah, so I will stop recording. I hope everything went